Hello, I'm Robert Toomey, a research developer working at the Cooperative Institute for Severe and High Impact Weather Research and Operations. This is an update covering the continuing progress and work on the fusion algorithm, in particular working towards getting closer to W2merger output. Our current goal has been to design a volume value resolver plugin that closely matches the output from W2merger. In our initial engine design, we made a 2-tilt linear interpolation plugin, which was a proof of concept. However, our operational W2merger is significantly more complicated in how it generates values. After this presentation, you'll have a greater understanding of how W2merger generates output values, as well as changes to the engine that were required for us to reasonably match it. So let's get started. So first, a quick overview of what we'll cover. The problem of overlapping beam width patterns is something we missed in the first alpha design. This led to changes in how the elevation volume works, as well as changes to the volume value resolver. W2merger value generation involves various stages and methods of processing data. The first is a pre-processing or filtering of radial set data. The second involves an S-curve interpolation or extrapolation that we will look at, and the third is a combination method of contributing values. This leads into a discussion on the elevation weight threshold used for this, and finally we have some comparison pictures for group discussion. So we've previously talked in detail about our stages of the merger process in other presentations, but to very quickly recap, we have three main stages. The first projects and combines single radar moments consisting of a volume of elevation scans into a CAPI form of data. Basically, it is a mathematically complex polar to Cartesian projection and value weight system. The second stage combines N radars into a 3D product covering a conus or larger area. And finally, the third stage is running data processing algorithms that use this 3D product to process and generate more products, such as an ecotop output, among others. So the responsibilities of the elevation volume plugin include keeping a collection of elevation angles in space and time, using some method to determine what is part of a current set called a virtual volume. It is also responsible for quickly searching and returning the elevation angles surrounding a given virtual angle of a sample location. For example, if your VCP and current virtual volume has a 0.5 elevation and a 1.3 elevation, then a request for a 0.7 virtual elevation will return the 0.5 that's below and the 1.5 that are above as your upper and lower contributing tilts. The necessary changes for this included expanding the search to include more than the closest two elevations. All N tilts of a volume in theory could be used to calculate the value at a sample location, but in practice a maximum of 4 are practical. This is because multiple elevation tilts can overlap the same area in space. For example, given a VCP of 35 with a 0.5, 0.9, and 1.3 elevation, all of these with a beam width of 1 degree can cover a sample location, say at 0.8 degrees. This is not taking into account terrain blockage or missing values in tilts. The responsibilities of the volume value resolver plugin include recalculating or calculating the values and weights for each sample location in the 3D output CAPI. And it does this for each of the layers, for each of the 33 layers. It gets a database about the information known at the virtual sample location, as well as a collection of elevation angles from the elevation volume plugin. The changes from multiple tilts also affects the way this plugin works as well. Given a set of contributing elevation angles for a location, the resolver can query information about any tilt of interest. This provides information such as the data value of that tilt and other meta information. It is then up to the volume value resolver to mathematically combine the values as it sees fit. Basically, we also need to be able to query information from multiple tilts for a sample location. N tilts may be too much CPU for now, but it could be possible in the future. The assumption is that data values that affect the sample point are local in nature, with diminishing effect with distance from the sample location. So here is a subset of the code example of the value resolver database. The first section here is meta information about the sample location. So we have things like the virtual azimuth, virtual elevation, and range, among other values for that location. The second part of the database is a per layer or elevation option. So at the bottom, we have information, say, for an elevation above us. These are usually requested on demand by the volume value resolver. Currently, the resolver can query up to 4 elevations, or 2 tilts above or below the sample location. So the values here would be unique for each elevation in the volume of interest. Using this information, the volume value resolver's goal is to combine this into a final value and weight for the virtual 3D location. So now we can move on to the particulars of what W2merger actually does to generate output values. The first thing done is that a moving average pre-filter is applied to every incoming radial set. This is done before any processing or use of those data values. It uses a scale of n starting at the radar center and moving outward along each radial. The effect seen is a despeckling or smoothing of the output image. The scale is calculated using the size of the output conus cells versus gate width of the radial set. For example, a 250 meter gate width and a 1 kilometer conus gives a scale of 4. Feedback given so far, we've seen that some like this despeckling and some do not. So currently we've added the -- pre-smooth option to Fusion to toggle this ability. This could possibly or probably be a more general pre-filter plugin ability at some point so that other smoothing methods could be experimented with, maybe before and after output generation even. So let's see a picture to get a clear idea of what we just described. Here is a simple original picture of the May 3rd, 1999 radial set data. And you can see that there's nothing being applied here. Now, if we do a scale of 2, we can see that it's starting to smooth or despeckle the values. If I continue to go on, now we're at a scale of 4. So for the 250 meter gate width and a 1 kilometer conus, this is currently what is being applied to all radial sets in the current W2merger. We can debate if this is a good thing or not, but this is what is happening. Here we have a scale of 8. And finally, we have a scale of 16. You can tell as the scale increases that the values of the moving average have a dampening effect of the output values. This in turn will smooth the final W2merger conus output. The effect on final merge data is subtle, but it's noticeable. Here we see the smoothing effect on the left versus the non-smooth image on the same storm on the right. As we said, this could be an option depending on preference and also a plugin ability to allow different types of pre-filters to be applied. This feels almost like a mini QC process that is being applied before any merging takes place. This could even be applied to data in a separate algorithm before even being sent to merger or fusion. Currently, though, this filter is extremely fast to apply and has a low memory CPU cost. So the next thing to mention is the W2merger S-curve interpolation or extrapolation, depending on how you look at it. Basically, elevation radials resemble a cone in space and have a round cross-section that's expanding as you move away from the radar. So the S-curve here is an attempt to handle the nonlinear drop in beam strength as you move out from the center of the beam. So on the left side of this graph, we have a linear weight of 0, which when put into the weight formula gives us a final weight of 1, or 100% full strength. This strength drops down to about 50% at the half beam width distance. The right side at full beam width drops to about 0. Now you need something to use to scale off of. In this chart, we are using the beam width of the elevation and or the elevation tilt, and treating the elevation independent from all the others. So in this way, you can consider it as an extrapolation out from the tilt. It gets a bit more complicated in practice, however. So in the weighting formula shown here at the bottom right, delta is just transforming a linear percentage that we call alpha into our S-curve result. The numerator or top part of alpha here is just the angular distance you are away from that elevation. The denominator or bottom part of the formula is based upon either the beam width of the elevation or the spread between the elevation and the next elevation. For example, if you're sampling at 0.7 degrees and have a 0.5 degree elevation below you and a 2 degree elevation above you, then the spread would be 1.5 degrees. The beam width might be 1. So we are taking a percentage of total beam width or the spread. We also maximize which is taken, which is basically a fallback in cases where you aren't between two valid tilts. So this picture here shows where we use the elevation spread between two tilts versus using beam width as the bottom of the formula. We feel that the max of the beam width or spread is a strength and a weakness. The downside is that elevations are not fully independent if you use the spread. So data values are stretched between neighboring elevations. This pretty much matches using the beam width when the spread is tiny. Most VCP patterns have angles close to each other, so the difference between spread and beam width is very small. However, at high elevations, VCPs tend to spread out the distance between elevations, so using just the beam width will create missing rings since the values drop off faster than when using the beam width. The upside is that when there are large angle differences between elevations, data is stretched between elevations so that it visually looks better. However, it can be debated what the max spread between these angles should be, or even if the distance between tilts should affect value weight. So toggling between W2merger output and fusion output using a two closest tilt interpolation, we ran into two issues. The first is that only using the upper and lower tilt values works well when the elevation angles between tilts is high. Here we can see that fusion towards the middle of the radar looks pretty close to merger output. And I'll just toggle this real quick to show you. So in the middle of this, you can see that they're fairly close as I toggle between them. Okay, this is because this VCP has angles far apart at high altitude. So for a given sample point, there are only two tilts affecting it. However, going to the outside of the radar, say on the left side, you can see a ring effect that we believe is caused by multiple elevations being close enough to add to the weighted sum of the output. So in these cases, it isn't just two tilts contributing, but others as well that overlap the sample location. A third effect can be seen in places where the upper tilt may have legit data and cover the sample area while the upper may be missing data. This gives the north area in fusion that is missing versus the W2merger output. And I'll just show that again, describing those effects. So the final process involves the following. For each contributing tilt value up to 4 in the current engine, we calculate the weight of each value using the S-curve formula. These are then added to the total weight if greater than a threshold value. We also keep the total weight, the total value if greater than the threshold value. We also keep the total weight. This is a weighted average formula. The final value is the final sum divided by the final weight. So more values included tend to dampen or make the output less hot while also increasing the coverage area. The logic can be more complicated. For example, the volume value resolver could selectively choose which values contribute. Jen once mentioned that the idea of using upper missing unless the train is blocked, in which case you use the next higher upper tilt. So part of determining which values to include in the weight sum involves a chosen elevation weight threshold. And this corresponds to the -E option in W2merger and has a default value currently of 0.45. This means the values are contributed to the final weighted sum if the weight calculated by the S-curve formula is greater than 45%. An interesting note is that this also determines the missing mask. Even if values are bad, they still cover the area, so we mask it by turning it from unavailable to missing. Decreasing this elevation value threshold increases how many values contribute to a location and expands the area of coverage. So finally, the acknowledge page. The main acknowledgments with value generation come from the original merger paper, which mostly explains all this math involved. This paper was originally written by Lack, Travis, Kurt, Greg, and Arthur back in the day. It talks about the moving average and weighting, among other things, using these formulas. Karen, of course, has ran W2merger and Fusion now at least 10,000 times to generate output every time we've changed something. Ken and Jeff have generously given us the time to explore and work on this. And Nat has given us the difference tool, which we've used extensively for comparing old and new output. So action list here would be to work on the value resolver some more. We want to clean up and do some optimizations. Is it good enough? Is it time to focus on stage 2 and end radar? Tweak some long-term running feedback. We have to tweak it a little bit probably and change it a little bit over time. And maybe we get some interested meteorologists to look at this code. The code that actually generates the values in Fusion is only 50 lines of code, basically, that does all of it. And you can completely control the output values from changing those lines of code. We need a stage 2 alpha, multi-radar combination, and we're going to figure out how we're going to communicate between stage 1 and stage 2. The original used raw files. Maybe we'll use something else. We're still debating that. That design is going to come next. And of course, we'll continually clean up and improve the API. And of course, it's all built on RAPIO. And this year, hopefully, we'll have the lab officially on a new Linux OS, such as Oracle 8 or another, and NCO upgrade as well. This will allow us to finally move the MRMS code base to C++ 11 or 14, at least, and allow more modern code to be deployed. Currently, the code here is on GitHub at the following address, http://github.com, RE2me, RAPIO. There at some point, this will probably move to an organization to allow more control from others. And I can say, have a good day. Aha! But we have an addendum. We have lots and lots of comparison pictures. So I hope that you learned some interesting things about W2merger, and that concludes that brief part of the presentation on the math, code, and processes involved in calculating our output values. What follows are pictures grabbed and comparisons between W2merger and the current plugin math of Fusion. For the live presentation, hopefully you all have a PDF so we can discuss issues and changes. Here in the video, we'll just briefly and formally look over them, so let's take a look. So starting with KATX 0.5, or basically half kilometer merger, we're going to look at the half, we're going to look at the 2, and we're going to look at the half. So here we have a 0.5. This is Fusion, and we got merger. You can see that they're fairly close. And then you've got difference graph. And where we have blue, that's where merger, or excuse me, that's where Fusion is actually got a little bit more data than merger, and red is, bright red is where merger would have something that Fusion does not. And we can just continue to go through this. We're just going to go. This one's interesting here. The Fusion one here, we got that green area in the bottom left. The only problem I had with these images, I wish we'd had time to do like a gradient color map versus a boxed color map, because values that are very close to the transition in the color map can give you that little jump. So here in that bottom left where that green area in Fusion is because those values are very close to the, looks like the 20 dBz mark. So if you get a 20.1 or a 19.9, it'll be on one side of the box or the other. So you get those little transition effects like that. But the difference graph will show you that the values are actually not that far off from each other. This is also showing like, I think Karen picked this one because there's some terrain blockage going on here too, to just kind of give us an idea of how close the terrain blockage algorithms are. And they look pretty reasonable. We'll get into some more weather. And like I said, you should have a PDF for this. So, or if someone's watching this video, of course they can pause it if they want to look at a picture more in general. So I'm just going to go through each of these a little bit. I like the look of this one. We got a little blue line and red line in the top left there. There's a slight rotation between Fusion and W2merger right now. It's a very, very subtle clockwise rotation of Fusion. And I think that's because the radial set lookup resolution is only set to, it's only to 0.1 degrees. So there's a little bit of floating round off there. So I've been thinking about trying to rewrite the radial set lookup to make it more accurate. And we'll just keep going there. You got that slight bit of terrain. And the difference there looks pretty reasonable to me, at least. And we get more here. I'm very impressed that we're actually getting results that are as close as they are for the amount of effort involved. This one's also not bad. Difference graph there. This one here looks like Fusion's being slightly greedier, and that may be because I'm using the 4 tilts. I may have to change the logic to not be as greedy with inclusion of values, because it looks like we're getting a little bit more data in there. That's why we get these little blue rings there. That's because this is close to the center of the radar, so these are the high angles. So we get a little storm there. KPOE 2.0, Fusion. Difference there, not too bad. Got a 4 kilometer merger, 4 kilometer Fusion. It's also not too bad. This one has a little storm to the bottom. And, you know, the nice thing is we're not getting, it looks like we're getting pretty close. So, okay. So that's the end. So that was that's the end of the discussion and suggestions for future value resolver work. We'll have to come on here, and we're also going to do the discussions on stage 2. And like I said, we have the value, we have the PDF, which we will, in the live meeting, of course, we will go over this and we can look at different pictures and discuss more in detail on that. And I might even provide a link for the PDF if I can on the YouTube page. But thank you for your time, and I'm glad you learned something, hopefully. And see you next time.